So in this talk, we're going to talk about optimizing AI in some specific ways that can take you from rag to riches. So we're going to start out with some basics, and then we're going to talk about how we can optimize our RAG pipelines for efficiency, for relevance, and for cost savings. And so even if you're brand new to AI, you should learn something from this. If you're a veteran, you should also take something away from this. And so who am I? I'm Jesse Hall. I'm a staff developer advocate at MongoDB. I've been there for about 3 years. And you may also know my YouTube channel as well. By the end of this talk, I expect to have about 40 more subscribers or so. So appreciate that. So even though I do work for MongoDB, this talk is not about MongoDB. This is everything that we discuss is applicable to any tech stack that you choose. So we're going to go over all of the things that you can apply to whatever tech stack you use. We're going to look at a brief history of AI very quickly, and then an introduction to Retrieval Augmented Generation, why it's so important, how search and retrieval it also relates to RAG, and why the traditional RAG, when we say traditional, it's only, how long has it been around? A year, 2 years, I don't know. But why traditional RAG isn't enough. And then how we can optimize our RAG pipeline for both accuracy and cost. And so throughout this talk, there's going to be several resources that I'm going to share with you through QR codes, so have your cameras ready if you want to dig a little bit deeper. So let's go ahead and talk about the evolution of AI. Analytics. The early days of computing, applications primarily relied on analytics and to make sense of data, and this evolved analyzing large data sets. And so the insights would be extracted from these data sets to inform business decisions, and this process was very manual. And so as computing power increased, became easier to analyze these larger data sets, and that's what brings us to batch AI. And so batch AI, the focus shifts to machine learning, and traditional batch AI involves training models on historic data and using them to make predictions or inferences about future events, about how users might interact with your applications in the future. And so the more data that you feed it over time, the more powerful it gets, the better the predictions get. And the more accurate these predictions become. So as you can imagine, it's really powerful. If you can predict what's going to happen tomorrow, you can make really good business decisions today. And so batch AI, as the name implies, it is run on a schedule, offline, and it's analyzing historic data to make these future predictions of future events. But this is where the problem with batch AI is, because it's trained on historic data. It doesn't have access to real-time data, to proprietary data, to your data. And so this is okay for certain use cases, but most applications are going to need real-time data. And so that's where real-time AI really represents a significant step forward, because this approach involves training models on real-time data, making predictions or inferences in real time. And so that's particularly useful in fraud detection, for instance. When that real-time data is very important, because what good is fraud detection when the person defrauding you has already gotten away with it, right? So the next stage is generative AI, and this really represents the cutting edge where we are today. This could change tomorrow, who knows? But this approach involves training models to generate new content. So these models are not simply making predictions about the future; they're creating the future. And so this can be images, text, video, sound, and whatnot. And fun fact, of course, all of these images were created using DALL-E. So over the years, we've seen AI evolve from a very manual process, and it has very rapidly evolved in the last couple of years. And this really is shaping the way that we interact with technology every day. And so this is why we really need to understand AI and how we can implement it into our applications and our use cases. So let's dive in a bit. You've probably heard of this thing called GPT, Generative Pre-trained Transformers. These are the large language models that perform a variety of tasks, from natural language processing, content generation, even some forms of common sense reasoning. So these are the brains that power our applications. They make them smarter. But there's a catch with these LLMs, these GPTs. They're incredible, but they aren't perfect. You see, one of the key limitations is their static knowledge base. They only know what they were trained on. We know that there are some integrations that allow them to search the internet for newer information, but how do we know that that information that it's finding on the internet on its own is accurate? They can also hallucinate very confidently. And so how can we minimize this? And they can't access real-time proprietary domain-specific data, and that is a big limitation. And so this is one of the reasons why we can't rely on these LLMs as they are. And so this is especially true in the business context when that up-to-date information can be a game changer. It will help us to make better decisions. This is more adaptable, it's more real-time, and aligned with our specific needs. So we're not merely talking here about RAG, about leveraging, or we're talking about RAG. We're not leveraging just the GPTs by themselves. It's about taking our applications to the next level and making them intelligent and context aware. And that is where RAG comes into. So Retrieval Augmented Generation. And so we're augmenting our applications to make them smarter, to augment the LLM's capabilities on its own and boosting their capabilities. And so this is also where vector search comes into. So with vector search, and again, this is not MongoDB specific. There's many different vector search platforms, but vector search can augment that performance and accuracy of those GPT models by adding a memory or a ground truth to help reduce those hallucinations, provide that up-to-date information, and allow access to our domain-specific data. So maybe a lot of you already know what RAG is, but this is the point when we're going to go through a basic intro to RAG, and then we'll talk about how we can then optimize RAG. So what is involved in Retrieval Augmented Generation? First off, we have to understand what vectors are. So vectors are the building blocks that allow us to represent complex multidimensional data in a format that's easy to manipulate and understand for the system. The simplest explanation is that vector is a numerical representation of data. It's an array of numbers. That's basically what a vector is. And so these numbers, they are coordinates in an n-dimensional space, where n represents the number of numbers, the amount of numbers that we have in the array, right? So you'll also hear vectors referred to as vector embeddings or just embeddings. And so a quick brown box translates to a very, very long array. It's cut off at the end, but in many cases, it's 1,536 floating point vectors in that embedding. So here's a real life example of vectors in use. So you go to the store and you're looking for something, you find an employee, you ask them, where do I find the light bulbs? They say aisle 30, bay 5. So that is a two-dimensional vector in use in real life. You'll also notice in stores that the light bulbs aren't just strewn around the store randomly. They're strategically placed. And that is, again, how we store our vector embeddings. Just like this, instead of two dimensionals, there's multi-dimensions. Another example is in games. So 2D and 3D coordinates are used to locate objects in the game world. Also used to detect proximity and collision detection. And so this same kind of math is used in vector search to find the similarity between different vectors. And if you're a Stargate fan, any Stargate fans? No? Okay, there's a couple. The address is made up of at least 7 chevrons or dimensions. These are just like vectors, and to locate stargates in other galaxies, you add an 8th or a 9th dimension there. And it's just like a telephone number's area code or country code, where you can see how this adding dimensions, it significantly increases the size of that virtual space that we're now using. So again, what makes vectors so special? They enable semantic search. So in other words, they allow us to find information that is contextually relevant and not just a keyword match. And so these data sources, they're not limited to just text. These, again, can be images, video, audio, and so on. And so how do we get these? How do we create these vectors, these embeddings? So this is done through an encoder, also known as an embedding model. And so the encoder defines how the information is going to be organized in this virtual space. So there's different types of encoders depending on your use case. There's different encoders for text, audio, images, and so on. Again, sometimes these are also, most of the times these are referred to as embedding models. And here is your first QR code if you want to learn a little bit more about embedding models and choosing the right embedding model for your use case. There's a great resource here written by one of my colleagues. Take a sip of water while you're doing that. All right. So what does this look like in practice? So first of all, we take our private, our custom data, and then we split that data into chunks. And then we go to our embedding model, we create those embeddings, and then we store them into our vector database. Again, these could be PDFs, they could be images, videos, text files, markdown files, whatever the case might be. And this entire process here is the ingest, basically, of taking your proprietary data and saving it as embeddings, as vectors. The first process of text splitting, or chunking as it's called, is actually very involved, and there's no one-size-fits-all approach to this. So this is another great, excellent article helping you to choose the right chunking strategy, depending on your use case. Give everyone a second for that. All right, wait for the phones to go down. All right, so once we have our embeddings for our custom data, we can now accept user queries. So the user is at the top there. They are initiating a prompt, a query, a natural language query. We then send that to the embedding model, the same embedding model that we sent our custom data to, because we need to put that user's query, their natural language query, into that same vector space as our information, so that we can then use vector search to find the relevant chunks. After that, when we get the embedding of the user's prompt, we do the vector search, we find the similar documents, we send that then to the LLM to answer the question using the documentation or the chunks that we found in our knowledge base. Then the LLM answers the question based on our additional context and sends that back to the user. So this right here, this is RAG. This is the workflow of RAG. So now, when we get those chunks out of our vector database through vector search, we can then do anything that we want with that information. We could summarize it. We can summarize the answer using the LLM. We could add links to specific documentation, or whatever the case might be. Sky's the limit. This is kind of where prompt engineering comes in, which we'll look at in a little bit. So imagine, your application has an intelligent chatbot. With RAG and vector search, the chatbot can pull in this real-time data, maybe let's say the latest product inventory, and they can use that during a customer service interaction. So with vector embeddings, we're again making our chatbots or our AI agents, or whatever the case might be, more smart and more adaptable and context aware. For instance, if something is out of stock, it would know right away not to recommend that, etc. So we can also, this is the one part that I'll speak about MongoDB, is that if you're storing all of your vectors in your vector database, why not store all of your other metadata? So this is one of the key features of MongoDB, that storing your metadata along with your vectors, and we're going to see how that comes into play a little bit later down the road when we're optimizing things, because we have this extra metadata that we can also use before vector search. Okay, so far we've talked about the basics of RAG, and now we're going to look a little bit at search and retrieval, which is similar to RAG. And we're going to see how this can maybe tie into helping us make our RAG pipelines a little bit more optimized. So anyone remember this guy, IBM Watson? IBM Watson was really ahead of its time. It got some criticism, but they essentially combined search and retrieval with natural language processing to answer questions. That's basically what RAG is. So this was RAG before RAG was RAG. And then we have these virtual assistants. Now, there's a lot of efforts underway to make these better than they are today, but so far they're only able to do a limited number of things. They can retrieve data through common API sources like structured data sources like calendars, weather services, restaurant finders, map information, and so on, right? But anything else that's doesn't have like a structured API support, they're just going to say, I'm sorry, I can't help with that, right? And then this is maybe the most successful use of retrieval in AI, most impactful maybe, is recommendation systems. You see these everywhere. So they recommend new music for you to watch. They recommend skincare products that your wife didn't know she needed. That's actually a screenshot from my wife's Amazon. So recommendation systems are everywhere. And so this is another part of it. And retrieval augmented generation is where we actually use search and retrieval to get pre-trained large language models to answer questions that they were not trained on. And so this is, of course, DALL-E's representation of RAG. So with that, let's look at how we could reframe our thinking of RAG as a recommendation system to make sure that our results that we get out of our RAG pipeline are as efficient as possible, most relevant as possible as well. So the goal here is obviously to retrieve the most relevant documents or chunks from our vector database. What's commonly used is nearest neighbor search. So you have a multi-dimensional space where you have your query, and we find the nearest neighbors to that query, and we return those results. But let's see what would happen if we did this with a recommendation system that is meant to make product recommendations to a user. So it would reduce the search space, but how about dropping out-of-stock items or items that users have already purchased? So a standard recommendation system wouldn't be able to do that. Or predict how likely the user is to purchase the item that you're recommending. The recommendation system alone wouldn't be able to do that. Or how about ordering or sorting the items in a logical way? Again, that system wouldn't do it on its own. You'd have to bolt on extra functions to do these things. And so let's apply that same thought process to RAG. So if we use this one-step process, the nearest neighbor search in RAG, again, we could reduce the search space. But what if we want the LLM to filter out results based on the latest information? The standard RAG approach would not be able to do that. Or incorporate feedback from users, their maybe previous interactions with the LLM. The standard RAG system would not be able to do that. And even here, the most relevant information near the top is important because there have been some research that shows that LLMs tend to focus more on the beginning of their context window when they're answering questions. So we always want to have the most relevant information towards the top of our request. So if we use this one-step process, we're not going to achieve everything that we might want. So how can we make this process a little bit better? This is kind of makes us want to add some extra steps here to augment the standard RAG pipeline. So what we'll do is first add a filtering stage. So with the filtering, we can make sure that we're only retrieving candidates that we know we want to put through this RAG pipeline and eliminate anything that we don't need. And then after that, we'll go ahead and do our standard nearest neighbor vector search. And then after that, let's add a scoring step. The scoring step will allow us to incorporate user feedback or allow us to use other models to rescore our chunks. And then finally, an ordering step, again, to make sure that we have the most relevant and highly ranked information towards the top of that context window. So this is the improved RAG pipeline that we're going to talk about. Let's dig into each of these steps and see what each one can help us add. So the filtering stage is going to basically, we're going to build like an allow list. I mean, filter out anything that you know does not apply. And so this is going to increase accuracy and decrease computational load because we're not sending as much information. Instead of sending the entire knowledge base through vector search, we're filtering it first to only things that we know is going to allow the LLM to answer the question, so whatever is in context. And so there is an asterisk here on the filtered requests because there are issues if you're too restrictive. So if we filter out too much context, we could reintroduce hallucinations. So the short answer is don't be too restrictive on the filter. And so you might be wondering also, when is the best time to filter? Is pre-filtering better than post-filtering? And so we have an example here. So the yellow dot is our search query, and then the green dots are some chunks with vector similarities. So let's say that the user has indicated that they only want movies. This is a fictional movie database, right? So they only want movies with an IMDb rating greater than 7. So that is our filter. And if we apply this as a pre-filter, the K is set to 2, so that means it's going to return the top 2 results. So then the filter will exit when it finds these 2 results because they are above 7 IMDb rating, but they aren't the highest relevance rating. But we'll see that it's going to return those 2 because we had that filter first. If we add that filter afterwards, it would find these 2 because they're the most relevant. But if we look at them, they are less than 7 IMDb rating. So it would find these 2 and then filter them out, and it would return nothing. So in most cases, pre-filtering is going to be the way to go. And again, this is kind of comes back to the use case of MongoDB. This is where we have this extra metadata. So the IMDb rating is one of those pieces of metadata that we are using right there in that same pipeline to filter on that first and then send it to vector search. All right, so now let's talk about the top K similar chunks or nearest neighbor search. Now, there are different search methodologies. We are used to vector search, right? That is generally what we use in vector search, but let's take a look quickly at another search methodology, which is called lexical search, sometimes also referred to as full text search or keyword search. And so lexical search allows us to find things based on keyword, right? And then vector search obviously is contextual similarity. And so we're going to use vector search anytime we know that the input is ambiguous. We're not sure exactly what the person is going to be searching for, but if we know exactly what the person is going to be searching for, such as maybe a year or something like that, we could use full text search to filter our results as well. But users interact with RAG systems like chatbots using natural language queries. And so we don't know exactly what they're going to type in. And so that is why lexical search is generally not ideal for this. Because if we were to send this through lexical search, give me a recipe for apple pie, it might return results for apple. It might return results for pie. It might return results for apple pie. Who knows? And so it's not really going to return the most relevant using keyword search. So again, that's why vector search is generally what we use. But I wanted to call that out because we don't want to count lexical search out completely. We're going to talk about that in just a second. So we do have a small problem here, though. Vector search is much more computationally expensive than lexical search, but it's much more accurate. So the thing that you want to always be aware of is that you always want your RAG pipeline to be as accurate as possible. So we're always trying to optimize for accuracy. But every time we optimize for accuracy, it's going to increase the computational load slightly. And so and this load is more expensive because of those distance calculations that we have to do on those multidimensional vectors, and finding that is, and we have to put all those vectors in memory as well. And so the computational load goes up significantly there. But again, don't count lexical search out completely. The next stage of our pipeline is scoring. And so again, we want to, each of these stages, we want to continue going right on that accuracy axis. And so one thing that we can do is hybrid search. So this is a combination of traditional keyword lexical search and vector search. And so with this, we can really optimize for contextual similarity and important keywords. So how does this work? So again, we take an example of a movie database here. We have an object with some fields in it, and we could generate embeddings for the plot field, for the plot text, and then create a vector search index on that plot embeddings field. And then we could define a lexical or full text search index on the plot text, right? So we have two different indexes going on there. And then we take the user's query, we generate the embeddings, we do vector search just like normal, we return the most similar chunks using the embeddings, but we also run the keyword search on the plot text itself. So then we return those, we combine them, and we generate final scores based on the two combined together, and that will give us an even more accurate result of information that we get back from our database. Another thing that we could add is user feedback. I've seen this in ChatGPT, for instance. Anytime they're beta testing something, they'll give you 2 different versions of it, or they'll whatever, and then you can do thumbs up or thumbs down. So we could return to the user the references, the actual chunks that it used, and then have the user tell us, was that good or was that bad? And then we could store that in our database, and then an upvote would increase, boost its score, a downvote would decrease its score, and that way we can kind of train our system as we go as well, based on our user feedback. So basically, hybrid search, again, we move to the right on the axis of accuracy, and a little bit more computational load because we're doing both lexical and vector search together. Now the last stage is ordering. So again, we want to make sure that we have the order with the most relevant at the top. Ordering is going to further improve the retrieval quality, but again, it's going to be another slight uptick in computational load. But again, this is okay because we want our RAG pipeline to be as accurate as possible. So if we didn't have a re-ranking stage and a reordering stage at this point, the order of retrieval would be set by the embedding model and the scoring algorithm, both of which are not really optimized exactly for relevance, right? And so there are re-ranking models. These are specific LLM models that are made specifically to calculate the relevance between query document pairs. And so we do this final re-ranking here, and now we know that we should have the most relevant information towards the top of our results, again, which is an important factor when sending them to the LLM for generation. So the re-ranker will assign those new relevant scores, and then that is a more accurate RAG system, a 4-step system to make your RAG system more accurate. And so next, let's talk about how we can optimize for money. How can we bring the cost down a bit? So this is where we talk this RAG to riches. How do we bring in the riches? How do we reduce costs for our organization? So we're going to talk about a couple things: prompt compression and vector quantization. So first, prompt compression. There's a lot of different prompting strategies out there, like in-context learning, chain of thought, React prompting, and getting the appropriate and quality responses back from an LLM is really an art form, right? This is the term prompt engineering. And so most of these prompting strategies involves sending a wall of text to your LLM as input, just a huge amount of text. And LLMs with very large context windows are really becoming the new norm. It's common to see an input size of 100,000 tokens, in some cases 1 million tokens. And this might be useful in some use cases, but utilizing that full context window on a REST API call can make the bill skyrocket pretty quickly. So LLMs with large context windows, they have their place in some real world applications, but there is the operational cost to consider. For example, consider this $10 per 1 million tokens. In an application like Airbnb, they have millions of visitors every day. That operational expense from the volumes of interactions alone would be so much. And so, not to mention that there is also an increased latency because we're sending all of this text to the LLM. The LLM has to take time to process all of that text and then send back the answer. So reducing the amount of tokens or the amount of words that we're sending to the LLM can actually help us with latency as well. And so as you continue building AI applications, you're going to come across this term or idea of prompt compression, also known as token compression. And so initially you might think that you're not going to run into that situation. Your app is not going to get that much usage. But building robust AI applications, it really requires us to think ahead of scalability and solving issues that might become bottlenecks in the future. So it's something that we should consider at least. So what is prompt compression? So prompt compression is the process of reducing the number of tokens fed into the large language model. And so just reducing the amount of words that we send it. So your goal here is to closely match the output compared to the original uncompressed prompt. So here's an example of the original prompt and the compressed prompt. So the compressed text has the essence of the information that is in the original text, but uses less words, so less tokens. Now, the advantage of utilizing prompt compression techniques is its ability to maintain the general information of the uncompressed prompt, but just significantly smaller. So we do need to be aware, though, that prompt compression can suffer information loss because we are reducing the amount of words. So there is going to be information loss, especially loss of information that's rarely mentioned in the text. That could be excluded. So it's important to understand not to compress too much. So there is a fine line there, again, based on use case and testing. But with prompt compression techniques, we can go from an uncompressed prompt of 50,000 tokens down to 10,000 tokens. Again, through testing, you would want to ensure that the same length and quality output is retrieved from the compressed prompt as you get back from the uncompressed prompt. So again, don't be careful not to overcompress. And so this is something that we'll have to fine tune in our evaluation and testing phase again of our application. There's no one size fits all to any of this. It's all based on your use case. And so testing is very important. And so here's another resource for you on how to evaluate your LLM application. So how to test it, make sure that you are getting the most accurate, relevant information back from your LLMs. All right, so we talked about prompt compression. Let's talk about reduced representation vector quantization. That's fun to say, right? Basically, this is mathematics. It's a way to alter your vector embeddings in a way that reduces its size on disk and in memory. So we talked about prompt compression. That's going to save you money and reduce latency when you're interacting with the LLM itself. Vector quantization is going to save you time and reduce latency when interacting with the database. So why is vector quantization needed? Well, let's look at the memory required for indexing floating point vectors. So this is the RAM required to index one 1,536 vector dimension embedding will take up about 6 kilobytes. 768 dimensions, about 3 kilobytes. But in this chart, you can see how this quickly gets out of hand when you get into the millions of vectors. So with 10 million 768 dimension vectors, we're going to use about 30 gigs of RAM. 10 million 1536, that's about 60 gigs of RAM. This is 130 million gecko vectors, and this is 390 gigabytes. And then 130 million 1536 dimension vectors is almost 800 gigabytes of RAM. So that is, for MongoDB specifically, that's the upper limits of the dedicated search nodes that we provide. So that is the problem. What's the solution? Vector quantization. So notice here in this vector embedding, it is floating point vectors that is in this embedding. And so floating point numbers, they take up more space. So how do we reduce the representation of these vectors without compromising their representational capacity? So a popular method, again, is quantization. And so in this example, we see how going through the quantization method is going to actually change these from floating point numbers to integers. So it's kind of like taking this image and trying to represent this image with less data. So the goal here is to represent this image with less data in a way that we can still identify what is in the image. So one way to do that would be to turn it into grayscale, right? So we don't need the color data in order to recognize that that's a puppy, right? So we can take that data out. It's still, based on our use case, it's still achieving the result that we needed. So in this case, we're reducing by 3x the space needed to store this because we're removing effectively the RGB values from the image. So we're removing unnecessary information based on our use case. And so it's important to understand that we are removing information. We're removing context. But again, in this situation, it's okay because we're just trying to identify what's in the picture. So it's similar to when converting floats to integers. What's particularly useful about vector embeddings, though, is that they represent abstract concepts inherent in language. And so this allows this method to be used even more extensively. So in the image, we were dealing with basically three dimensions of vectors, the RGB, and making it grayscale. In a vector embedding, a lot of times you're dealing with 1,536 dimensions. And so there might actually be more information than is needed in those floating point vectors. And so we might be able to get away with integers in that case without compromising the ability for the large language model to provide us with accurate results. So there are a couple of different types of vector quantization. There's scalar quantization, which involves going from float 32 to int 8. And so what we do here is we take the min and the max, we create equally sized bins or buckets, and then we map the existing floating point numbers into those bins. Let's see that in action. So we have three different text chunks here with their vectors. We find our min and our max within all of the vectors. Then we create those equally sized bins, and they range from 0 to 255, so int 8. And then we map all of our vectors into those bins. So 0.743 becomes 255, 0.322 becomes 140, as negative 0.189 becomes 0. And then we just keep going through all of our vectors until we have our scalar quantized vectors. It's really that simple to go from float 32 to int 8 vector quantized vectors. So that is example 1. Example 2 is called binary quantization. So instead of float 32, we're going down to one byte for each dimension. And so an even further reduction in space, which results in cost savings. So again, it's basically the same process, but instead of the sorting these into bins, we get the median value, and anything above that is 1, anything below that is 0. And so we could just do that same thing. We go through all of these until we have our binary quantized vectors. Now, I do want to quickly call out here that we went from float 32, which has a huge range of values, and it has a lot of information, down to a single byte. So obviously, the question that's going through all of your heads is, we just lost a whole lot of context there, right? Didn't we? And so you're right, we did. We're representing much less information. But think about this: if you have 1,536 dimensions, you're still representing a massive amount of data. And so that's not to say that it's not going to impact your accuracy at all. This is just another one of those knobs that you have that you can tweak depending on your use case, because in most use cases, the full fidelity of vector information is not really needed. So it's just a matter of deciding if binary quantization is too much for your use case, and if so, use scalar quantization. So let's look over, this is the end of it. What did we learn? There's more to RAG than just nearest neighbor search. You should pre-filter using metadata to help reduce the computational load and decrease latency. Full text search has a place. When it comes to RAG, using hybrid search, use that re-ranking step as the final step to ensure that you have the most relevant results at the top of that context window. It's very important to get good results. And then carefully use prompt compression to save money, and reducing vector representation via vector quantization can make you rich, or at least save you some money. Last QR code, if you want to dig in deeper, what is an AI stack? So there's a bunch of different technologies that can be used to compromise your stack. And this goes into a lot of details into many, many different technologies that can be used. And wait for the last phone to go, and that's it.